It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farming Doing Nice Coffee.
Hi guys, welcome to this video. This one's going to be all about electronic configurations. Electronic configurations you'll sometimes hear referred to slightly differently as well. Sometimes you hear it called subshell notation as well. Okay, so in the exam, if they ask you a question to write the subshell notation for a particular atom or ion, it's doing the electronic configuration. It's exactly the same kind of thing. Alright, what I'm going to be talking about first is just basically where we get this convention from. So if you think about just a general atom, okay, the atom, you've got your nucleus in the middle, okay, so there's a nucleus containing your protons and your neutrons, and then around the outside, you've got these electron shells. So this is just a very, very basic idea or thought about an atom. Each of these electron shells can hold a certain number of electrons. The first shell can hold 2, the next one can hold 8 as you go around, alright, and the next one can hold 18. So you can have 2 electrons, then you can have 8 electrons, and you can have 18 electrons, and it keeps going. Okay? Each shell gets progressively bigger, each shell can hold more electrons. However, this is a very, very simplistic view or thought of what a atom looks like, because within each of those shells you actually have subshells. Okay, so you have different energy layers where each of the electrons can reside, and sometimes those electrons can move between layers, and that's where we get the colours from for flames, for example. So when we do the flame test, the reason we see colours is because we're exciting electrons to a different energy level and then they're going back to their original energy level. So we'll talk a bit more about that when we do the practical. So in terms of those actual subshells, alright, there are certain subshells that we have, alright, and these relate to blocks of the periodic table. So you've probably looked at the periodic table and seen that we have an S, a P, a D and an F block, and sometimes you see them referred to that. Okay, the S block, if we just have a quick look, if we just draw up the periodic table, very, very simple form, looks like this, okay, with this extra block down the bottom. Okay, this block over here, which is all your group 1 and 2 metals, right, that's your S block. Okay, over here, which contains your non-metals, which is groups 3 through to 8, VII, okay, that is your P block. The transition metals in the middle here, they are your D block, and right down the bottom, the lanthanide and actinide series, that's your F block. Alright, and that relates to basically their highest shell that they have. So the period number tells us how many shells there are, but the block they're in tells us what the highest shell is within those number of shells, highest subshell is. So what I'll do is show you how we write some subshell notations, and hopefully you'll be able to see how that actually relates to the periodic table and those different blocks that I've talked about. So first thing you need to know about is that we have each of those different subshells, and they can hold a maximum number of electrons between them. Okay, so remember I said that first shell, alright, of the electron can hold up to 2 electrons. The first shell of an electron is only made up of an S orbital. The second shell of the electron that goes around the outside is made up of an S and a P orbital. Now if you have a look, the S can hold 2 electrons, the P can hold 6 electrons, so that means that that second shell can have a total of 8 electrons in it. Okay, the first one can only have 2. The third shell is made up of an S, a P and a D orbital, so we start to split into those 3 separate layers. Okay, now an S orbital can hold 2, a P orbital can hold 6, a D orbital can hold 10. So in total that can hold 18 electrons. Okay, and then you keep going to the 4th and 5th and you start adding those F orbitals as well. We're never going to deal with F orbitals and writing electronic configurations. You just need to concern yourself with S, P and D. Alright, so that's how we're going to use the maximum number of electrons to write the electronic configurations. So to do that, what I suggest you do is you use this little chart. Okay, so this little chart here shows us the order of subshells, and it shows us how we actually use them to write electronic configurations. Okay, so you start down the bottom with the 1s, so that's the first one you go through, and then you go to 2s, and you start just working your way diagonally across it. So when you get to the exam, it might be worthwhile to write this up. So then we go 2p, 3s, 3p, 4s. Now it's important you note we get to the 4s before the 3d, and that becomes really important with transition metals, and I'll explain that in a minute. Then we go 3d, 4p, 5s, like that, and then we'd keep going with 4d, 5p, for example. However, the highest electron shell configuration you need to be able to write is for strontium, and that highest shell is 5s2. So that's the highest you need to go. So I suggest you sort of keep that nearby as you're starting to do this as a handy reminder. So I'm just going to move it up the top here as we start going through and doing some. Alright, so the first one I'm going to start off with is just a simple one, and in order to write the electron configuration you need to be able to find the atomic number off the periodic table. Okay, so I'm going to start with nitrogen, which has an atomic number of 7. So what I'm going to do is start to use this process just to go through the subshells and start assigning electrons in until I get to 7 total electrons. Because when we have no charge, okay, no charge, alright, the atomic number equals the number of electrons. Okay, so in this case here, 7, we're trying to get to 7 electrons in total. Alright, so I'm going to start with the 1s orbital because that's down the bottom, 1s. And if we remember from our little sheet, alright, the 1s can hold a maximum of 2. Alright, so we can have 2 electrons in that s orbital. Alright, so you might want to keep that little sheet with you as well to remind you about how many electrons each of these subshells can hold. So the s can hold 2, we've filled that up. We keep going, next we get to the 2s. Okay, the 2s, again the s can hold a maximum of 2. So far we've got 2 and 2, which makes 4 electrons. So we go to the next one, which is 2p. Now the p orbital can hold a maximum of 6, but we don't need 6. We've got 4 there, we need another 3, so this is going to be 2p3. And that is the electronic configuration for nitrogen when it's neutral. Okay, so you just work your way through that chart at filling up the shells as you go until you get to your atomic number, adding up these numbers across the top. So I'll show you a couple more. I'm going to move that to the side, sorry, just so I've got a bit more room. Okay, so I'm going to go to one that's a little bit bigger this time. So I'm going to go to chlorine, which is atomic number of 17. So we start with 1s. Alright, the 1s can have 2 electrons, so we fill that up. Then we go to 2s. The s can have 2. We go to the p. 2p, that can hold a maximum of 6. So far we've got to 10 electrons, so we keep going. After the 2p, we get to 3s. That can hold a maximum of 2. And then we get to 3p. That can hold a maximum of 6. But so far we've got 2, 4, 10, 12. We need 5 more to get to 17, so this is going to be 3p5. Okay, so all you do is you follow this chart, fill them up as you go. The highest one that you need to get to, if you remember I said, was strontium. Okay, strontium here, and see if you can do this yourself firstly. So I'd pause the video. All right, see if you can do it using this, getting to the highest maximum shells that you can. All right, and using the atomic number off the periodic table. Okay. So pause it, see if you can do strontium yourself, finding the atomic number off the periodic table, and hopefully what you'll get is this: 1s2, 2s2, 2p6, 3s2, 3p6, alright, I'm up to here, 4s2, then 3d, that can hold a maximum of 10, 4p6, 5s2. So there's your electron configuration. It has a total of 2, 4, 10, 18, 20, 30, 32 electrons. That's why its atomic number is 32. Okay, and that's the highest one you need to go to. All right, do them all the same. Okay, have a practice of them. What I'm going to show you now is how you do ions. Okay, so I'm going to go back to that one I had before of chlorine, 17Cl, and I'm going to introduce the first rule here. All right. And the first rule I'm going to introduce is that non-metals always fill highest shells when they form a charge, okay, when they form an ion. So chlorine, if you remember, was 1s2, 2s2, 2p6, 3s2, 3p5, okay? Now chlorine, all right, when it's in its ion form, it has 7 electrons in its outer shell, so it wants to gain 1 to form that stable octet of 8. So chlorine, when it's a 1 minus, all right, 1 minus means we've picked up 1 electron, Alright, so we need to put that electron into a shell, and they always fill the highest shells. So here we've got a P. P, as we know, can hold 6 electrons, so we can put that 1 electron into there. And that is the electronic configuration for a chlorine ion with a 1- charge. Okay. If we go back to our one that we had for nitrogen, nitrogen here was 1s2, 2s2, 2p5. Okay. Sorry, I can't count. 2p3. All right. There we've got our 7 electrons. Now here in the outer shell, in that we have 5. We know that in order for it to be stable, it wants to get to 8. So we need to add 3 electrons in here, which is my nitrogen has a 3- charge. So if we're adding 3 electrons in, that 3 becomes a 6. We now have a full outer shell, and that's the electronic configuration for nitrogen. Okay. So when you have non-metals and you're making ions, you fill your highest shells, just with the number of electrons that you need to get that 8 electrons. When you're looking at metals, alright, I'll introduce the second rule. Metals always lose their highest shell electrons first. Okay, so if we take a metal such as sodium, which has an atomic number of 11, its electronic configuration is 1s2, 2s2, 2p6, 3s1. Okay, what you need to do with this one is we want to get to a stable outer shell. It's got 1 electron in its outer shell. So we could either gain 7, which would be very, very silly to do because that's very hard to do, or it could lose that 1 electron. So they lose the highest shell electrons first. So we're going to take out this 3s1 electron, like that. If we lose an electron, we actually gain a positive charge. So that becomes a 1+ ion, that's why sodium's 1+. And the electronic configuration is actually 1s2, 2s2, 2p6. Now, if you've clued into that, you would have seen that the nitrogen that we did before with a 3- was 1s2, 2s2, 2p6. Okay? Those are exact same electronic configurations. Different atoms, okay? Different ions, I should say, but same electronic configuration. And both of those are exactly the same as another element. Alright, see if you can work out what it is. It's got an atomic number of 10, alright, and tell me what's unique about that element when you have a look at it. Alright, hopefully you've worked out what it is, and you can tell me why these have the same electronic configuration as this element here with an atomic number of 10. Alright, I'm going to leave this first video there. What I'm going to do in the next video is talk about transition metals and their electronic configuration. Thanks guys, bye.